Hello students. So this is an explanation of the parts that was given to you. So here, uh, this part of the problem, we have seen some of the problems, the theory part of welded joint. Here is another problem. Here you can see that here two plates are joined in this manner. This is one plate, okay, this is another plate, right? These two plates are this plate is kept over this plate, okay. It's kind of this plate is below and this plate is above that plate, okay. And we have joined both the plates with a welding shown in this black color, okay, the dark part. This part is the welding, okay. So here it's kind of a lap joint only, okay. But here you can see that the pulling force is in this direction, okay. And this part of the weld is perpendicular to this force, and these two sides of the weld are parallel to the pulling force. So here actually we will have both parallel weld, okay, and transverse fillet weld. This is transverse and this is parallel, okay. Now we will see that what is the required length of the what should be the minimum length of this parallel fillet weld, both sides, okay, either of them. So that it can take this load of 55 kilonewton. So 55 kilonewton will be the load here, so that it can withstand it. So highest amount of tensile stress of the welding material of this welding can be 70 newton per millimeter square, and highest amount of shear stress can be 50 newton per millimeter square for the weld respectively. Okay, now let's have a look at the problem. So you know this is the force, this is the shear stress. Okay, everything is given. Now this part, you see, uh, a plate 75 wide and 10 thick. You know, small h is the thickness of the plate, and small t is the small t is the thickness of this welding. Okay, the throat. Normally, in some cases, they are equal. Okay, but in case of this um, here you see parallel fillet, okay, transverse and parallel fillet weld, okay, we will take the thickness as 0.707 of h, okay. So this is the thickness actually. So here you know this formula. So for transverse fillet weld, the strength equation is this: P1 equal to 0.707 HL sigma t. We have seen this formula. So from this formula, since we have only one transverse fillet weld, we will use this and we will put down all the values. So h is given as 10. Length of that part is known here. It is given as 75 mm. Okay, and this is maximum the tensile stress, reliable one. So this is the transverse. This is the strength on maximum value of force that can be taken by this part, transverse fillet. Okay, so which is not 55 kilometer. Okay, so we will now uh, see this one for double parallel fillet weld. So here we have one parallel, another parallel. That's why it is double parallel fillet weld. Since it's a double parallel fillet weld, this will be 1.41 instead of 0.707. Okay, so for fillet weld it will be shear failure, so that's why this part is, this one is shear stress. Okay, so putting the values in this formula, we will get the strength as 707 L. Now L is unknown, we keep it like this. Now you know both, total force that is uh, just trying to separate the plates is 55 kilonewton, and the weld has to resist it. So the total resistance or total strength of the weld by this one plus these two has to be equal to 55, equal to this force, okay, force, because these are resistances here. P1 is and P2, these were resistances. So we will add them together and make it equal to 55. 55 kilo. Okay. Now from here we will get the length required. Okay, minimum length required 25.29 mm, so that we can, so that this load can take 55 kilonewton. Okay, exactly. Now we have to add 15 mm with this. Okay, so that we can start and stop properly. So adding 15 mm, starting and stopping of well run, we have this L equal to 45 and nearly 40.29, we take it as 45 mm. Next, we have this eccentrically loaded welded joint. Please read this part, whatever is given. Now you see, it is like just similar thing to the previous one. Here you see, here also this first part, this is the second part, joined together. But here we have pulled it along in this axis. Now here you see, again it is similar. There is one part, there is another part, joined in this manner. Okay, here one welding, here one welding, but here instead of pulling it along in this direction, okay, or downward direction, here we have pulled it away from that point, which will cause some eccentricity. Okay, I mean we are pulling this plate, whole other plate downwards, okay, with some eccentricity. Since you have already learned this in case of your riveted joint, in case of threaded part. Okay, so we will see this now how to do it. Here the thing is, the difference between rivet and threaded joints, etc., is that here we don't have a definite rivet or thread. Okay, in case of thread or say this metric threads, we had one, suppose one here, two here, three here, four here. Okay, but here the entire portion has the welding. Okay, welding. So to locate this Z, a center of gravity, in this case is not very hard. Okay, it's like you just take the half of, say suppose this is a total length of your welding. Okay, so middle of that will be the length of Z from here to here, from this edge, and from top. Okay, the total half of the length this much. Okay, part of the half of the width will be is Z. So G is your center of gravity for welded part, not for the entire part. Okay, so once you look at this Z from, from the point, sorry, from the point of application of force to Z, okay, to this center of gravity of weld, is that distance is called eccentricity. And we can just replace this whole thing. We have already seen many times that this is a force pulling downward through Z and the moment about Z. So to prevent the whole thing, what you have to do, you have to put an upward force, okay, upward force through Z, upward, and what else, and we have to put an opposite moment. Okay, it's like this. We have to put an upward force here, upward force through Z, and then opposite moment just to see, prevent the failure. Now here you see, uh, so what else here, actually instead of finding out the shear stress, shear force, primary or secondary shear force, since it's a moment here, I will just consider it like a moment. Here you see, uh, in general, this part, okay, this part here, we will only be interested in failure of the welding. Here you see, this part P, okay, P here, this will cause a shear failure of these, okay, welding part. Okay, first of all, so because I mean this force is passing through G, so that's why we will have to counter the shear force. First of all, this is called, since this is that shear force will be passing through Z, so divided by the area parallel to this force. Okay, the throat area of the weld, actually in this case will take. Okay, we'll see how to find that area, throat area. Okay, and this is just force by area. Okay, and then secondary shear stress is calculated using this. Since there is a moment, and that is also causing a shear stress only here, okay, in this case. So finally we will have another shear stress, that is a secondary shear stress. Unlike we did like shear forces, here we have shear stresses, okay. So shear stress tau 2 equal to m into r divided by, so this comes from your torsion equation, okay. So m by j equal to tau by r from that formula, okay. M is your uh, torsional moment, and this j is polar moment of inertia, okay, which is about this z, right. So here, you know, polar moment of inertia, since this plane here, this plane, okay, I mean that side into the board, that is x-axis, and perpendicular to that is y-axis. So here uh, we have this axis, okay, about which it is rotating, is z-axis, okay. So that's why this is polar moment of inertia. So here actually, let me tell you once, this is actually x-axis and this is y-axis. So the rotation is about z-axis, okay, z-axis, and that's why it is polar moment of inertia, change in angle. So here you see polar moment of inertia of all part weld about g. So rotation of this welding part about g, we have to find out. For that we have actually a little bit of derivation will give you this. Okay, so this is G, not C, sorry. So polar moment of inertia is given by this formula, which is the A is the throat area, L, small l is actually this part. Okay, small l is the length from here to here. Okay, and R1 is the length from upper point, any side, okay, any side of this welding. I mean, let me show you here in this problem. Okay, in this numerical, you see this part. Oh, sorry. L is not this. This one, L is from here to here. Length of the weld. Huh? L is length of the weld. And R1 will be this much. Suppose this is Z. So from here, from here to here is R1, or from here to here is R1. Okay, either from here to here is R1. You can see it here. Okay, this is R1. Okay, R1. Yeah, we have only shown the uh, welded portion. Okay, so let's have a look at this problem. So a welded connection as shown in figure is subject to an eccentric force of 7.5 kN. So this is the force. Determine the size of the weld if permissible shear stress for the weld is 100 Newton per millimeter square. So this is the combined shear stress is given. Okay. So what should be the size of the weld? Okay. So that means the throat area. I mean, sorry, the throat part. Okay, that is thickness T. Okay, that you find out, and then you find out the value of h. From here to here will be h. Actually thickness is c. This is thickness, okay, or throat area we call. This part is t and this part is h. Okay, it may not be clear to you, but have a look, this line here, okay, from here to here. Okay, quickly let me tell you, this part is t, this is t, we find t, and from here to here, okay, this part is h. Understood? This part is h and this part is t. So that is what we find out here. Okay, we have to find out that h part, this part. Huh? This is h, this is h. Okay, you can see this small triangle, perpendicular and base both are denoted as small h, and this part is in this, the hypotenuse is t. Okay, first we'll get the t first, then we'll get the hypotenuse part. Okay, let's see this problem. So let T is the throat area of the well. So here, first of all, we take this section. T is not a throat area; it is a throat thickness. Sorry. So throat area can be given as with this. Okay. Now you see 50. 50 is the total length. So if you can, a little bit consideration will show that if you see from this side, this welding will look like a rectangle. If you project it, no, this side, this slanted inclined part will, if you project it, it will look like a rectangle like this. So from this to this is T, this is T, and from here to here is what, 50. Okay, given in the question 50, here you can see this is 50. So 50 into T is the area of this part. Similarly, this side also we have that. So 2 into 50 into T, that is 100 T, that is the area. Fine. Now we have the primary shear stress, which is given by tau 1 equal to P by A. So this is the force, this is divided by area, which is equal to 75 by T. So here you see, this is the force and area we have found it. So we know how to find it, tau. Let's get to tau 2. Now tau 2, for that you need moment, that radiate R will look into that what is R, and now this is Z. So M is very easy to get. This is the force and the eccentricity. Eccentricity value is what? See, 100 from here and half of 50. That is 100 plus 25. Okay, 125 is the eccentricity. So 7.5 into 125 will be M. What is R? R is actually the distance from center of gravity of the weld to the farthest point of your welding here. So the farthest point of welding from G is this, all the corners. Okay, so that is R. Okay, so here you have to find out that R. This side is 25, this side is 25. So root 25 square percent of square will give you the value of R. So eccentricity moment you have found from this. Okay. Now what is left? That J. J formula I told you. This is the formula. A into L square by 12 plus R1 square. So here you see R1 is 25. Okay, it is clear from here. You see this is 50, so this will be 25 from here, and this is remaining is 25. So here area is 50T, 50T. Okay, into L is 50 square by 12. R1 is 25. Okay, so here J1, that is the polar moment of inertia, J, this is equal to, so 41,667. Okay, so now actually polar moment of inertia about the Z, this one, this part. Okay, uh, this is for welding one. Okay, see for each welding, so this welding actually, right now I'll not be able to show it in online class, but the thing is this part rotates about G, and just think that polar moment of inertia will be there for each weld. So this the for W1 weld, W1 is the first weld, W2 is the second weld. Okay, so for W1 we have polar moment of inertia J1. For W2 also we'll have polar moment of inertia J2, and since they are length are same, okay, they will have the same, and the distance from G is also same. That's why they will have the same moment of inertia. That's why total moment of inertia will be addition of these two. Okay, so J1 plus J2. We can write twice of J1 since they are same, and since we have got this 41,000 into 44,167 T, we double it so that we get the polar moment of inertia total. Since why did we double it? Because these two are same, and this is for the first welding part, this is the second welding. Okay, add them together, we get this shear stress. Now we have J value, everything we have. We just don't know the thickness, throat thickness. Okay, now simply this is another part to understand. Here you see this is upward shear stress. Okay, which is here. Again, look at this. This is the upward shear stress first of all, and each farthest point of the weld has to provide a opposite moment. For that, this will provide like this. This farthest point will provide like this, just like the just the way we have seen in your threaded part. Okay, so this is shown here. See, just like this. Okay, this one here. Okay, this one here, this one here, that way, and all each and every point of, I mean, farthest point will have tau 1 tau 1. Actually it is present everywhere, but we show it like this at the ends, the extreme points. Now say at one of the extreme point, let's say the topmost point to the left, okay, sorry, to the right, we'll have this tau 1 in this direction. So we have 75 by t, we have found this here, 75 by t, okay. And here you can see this is tau 2, which is uh, is 397.8 by t, which we can resolve it actually. Now how did we resolve this? This is 45 degree, 45. So 397.8 by t into cos 45. If you do that, then you will get 281.3. Okay, this side. Here also this is 397.8 by t sine 45. To do that, you will get the same because cos 45 sine 45 both are same, 1 by root 2. So you'll get these two values. Okay, we have resolved it. Now what we can do is, since this one, okay, this direction of this stress and this stress, okay, they are in the same direction, we can add them. So 281.3 plus 75 will give you 356.3, and this one is horizontal, so that will remain the same. Okay, I have actually mistakenly not written the tau divided by t part. Okay, divided by t is there, this divided by t. Okay, yeah, and this 281.3 divided by t is there, will not goes anywhere, so like this. Okay, so now you see, since this is the total one, so we can find the resultant tau now. Okay, what we just did is we have added this tau 1 and tau 2 to get this tau total. Now we have a horizontal component, we have vertical component. Just square it and find it out. So actually both of them have t divided by t. Huh? This divided by t is there. It is missed. I'm sorry that for that. So this will be ultimately 454 by t. Huh? So this is the total shear stress that has to be prevented. Okay, and the permissible shear stress that for the material, if material is 100, it is given. So this is the permissible shear stress. Okay, combined shear stress result. So which will be equal to 454 by t equal to 100. Okay, this whole thing, this is the shear stress that came out after calculation. Okay, and which should not exceed 100 mm as per the question. So we will just equate it to 100 mm and we'll get the required throat thickness. So that if throat thickness is 4.54 or nearly 5 mm, then your this part will sustain this I mean the full load can be sustained by this part and it will not fail. Okay, that is what we need to we have investigated from this. Okay. So I'll finish this part here, and the next part I will explain in the next video.